part 2 of section 2.4. So hopefully you took the time between pausing or stopping the first part and starting the second and went through these problems here. But at any rate, for part A, they want you to find the median, and this is where you have to understand and remember the median, the mean, the mode are all the same in a normal distribution. So right here, the 630 in the middle, the mean is the median. And then part B, within one standard deviation of the mean. So whenever they say within one standard deviation, you're talking about from 595 to 665 in this problem. And more importantly, 68% of the data is going to be within one. So then you just take the total number, which was given up here, there were 4,100 students, and multiply that by 0.68, or find 68% of that 4,100. And that gives you 2,788 students within one standard deviation. For two standard deviations, there's 95% total. And this is part of the empirical rule, 68, 95, 99.7. Sometimes they'll even call it the 68, 95, 99.7 rule instead of the empirical rule. But at any rate, however you get there, there's 95% within two standard deviations. Multiply 0.95 by 4,100 and you get 3,895. So this next one, this is not as trivial, 595 and 700. So this is where you want to come up to the graph. This is why it's so important to draw this thing. And you put 595 and you go over to 700, and then you add up in between these two all the percentages so you can find the percent within those two. Very common in these empirical type problems to have you do something like this. So adding up 34, 34, and 13.5, you get 81.5%. So move the decimal, you get 0.185 or 815, times 4,100, and then after you round, you'll get 3,342 students. So then going into part E, it's a similar idea, scored less than 560. So you come up here to the graph that you drew, which is going to help you get these problems right if you do it. And then from 560, you want to be less than that. So, less than that 560 would be these two scores, or the two percentages added together, 0.15 and 2.35. So when you do that down here, 2.35 plus 0.15 gives you 2.5%. Move that decimal two places to the left, multiply it by 4,100, and after you round, you get 103 students. So, it's so important, and I see students try to do these things without drawing out this picture, and they end up just like basically failing. It's horrible and sad. So like trying to do it in their head, and unless you're really good, you're not going to be able to do this in your head. And a lot of times people are trying to do it, they start reading through the problems, they don't know where to start, and it's like, just draw the picture. Save yourself a hassle, save yourself time. You're going to use the picture for a lot of the different parts. Just do it. It's a huge piece of this, empirical rule is just draw yourself a picture. It saves so much hassle. Anyway, that's my little soapbox for that one. So moving into z-scores then, because that problem before pretty much illustrates every type of problem that you might be asked to do in an empirical situation with a normal curve. So now with z-scores, when statisticians analyze data sets, sometimes they want to know if a certain data value is unusual or usual. And they'll measure this by looking at how many standard deviations away from the mean it is. So the z-score formula will determine this for you. So when you look at the z-score formula, what you're going to see is z, for z-score, equals x minus mu over sigma. So what you're doing here is you're finding the deviation up top, and you're dividing it by sigma. And when you divide it by the standard deviation value, it's going to tell you how many standard deviations would go into it. So for example, if you had like an x value of 10, a mean of, let's say, 6, the deviation would be 4. So what that's telling you is that your X value, your data value, is 4 units away from the mean. Well, then if you knew that your standard deviation was just 2, you would be able to divide 4 by 2 and get 2. And it's like, okay, well, there's 2 standard deviations away for that particular data value. So that's how the z-score works, is once you find the deviation, the true distance away, and then divide it by the standard deviation value, it'll tell you how many standard deviations away you are. And it could be decimals, it won't always be a whole number value, but that's how that basically works. So the data value is the X, the raw score. The standardized value, the Z, is what you get on the other side, which tells you, how many standard deviations away it is. If you're ever like, what's a z-score? It's how many standard deviations away you are, period. If it's positive, you're greater than. If it's negative, then you're less than the mean. So it's always how many standard deviations away you are for that Z relative to what's going on in that data set. And then the mu is the population mean. The sigma is the population standard deviation. So I can't stress this enough. This is really what the z-score means. And when you are looking at things like, what's considered unusual, it's all based on the number of standard deviations away, which is where the z-score is helpful. So typically, in a normal distribution, 95% of the data is within 2 standard deviations of the mean. And because the percent of the data outside 2 standard deviations is only 5%, statisticians often use 2 standard deviations away as the cutoff for unusual. So if you're looking at z-scores that are less than -2 or greater than 2, that's telling you that you're more than 2 standard deviations away on the low side or the high side. It's an unusual value. You're so far away from the middle, you're in that little tiny 2.5% on either side of that 95 chunk in the middle between the 2 standard deviations. That's unusual. So a usual value has a z-score between -2 and 2. So that is -2 less than the z-score less than 2. So in this case, and you might be saying, where's the equal to? And you usually don't see that with these, but in practice, if it's equal to 2, then it's still going to be okay. It's usually if it's outside the 2 standard deviations. So standardized test results in a local school district follow a normal distribution and have a mean of 630, standard deviation of 35. So kind of back to that one problem that we saw before. So what I want you to do is pause this video and answer the questions that follow using the z-score formula. Okay, so for part A, plugging in the given information, the z-score for a score of 702, that tells me if this is the X. They gave me the mean, the mu up here, the sigma here for standard deviation, and it's always X minus mu over sigma for your z-score. I encourage you to put parentheses around the numerator if you're doing this in a calculator, because if you don't, you'll get the wrong answer. Your calculator will think you just want 702 minus 630 divided by 25 or 35, not 702 minus 630 then divided by 35. So be careful with that. Put parentheses if you're typing this all in your calculator at once to ensure you get the right answer. And it'll be 2.06. So that tells me that I am 2.06 standard deviations away from the mean on the positive side, so going out to the right. That is unusual because it's more than 2 standard deviations away. So in part B, similar idea. They gave me an X score. The mean standard deviation stayed the same. And again, using parentheses, make sure I don't get the wrong answer for the z-score. And z here is -1.29. Well, Even though it's on the negative side, it's not negative 2 point something. So it is a usual value because it's within 2 standard deviations of the mean. And then the last one here, this one changes up a little. They gave you a z-score of 1.02 and they were looking for the x. This was the thing we didn't know. So they gave me the z-score here. They still had the same mu, the same sigma, and then we're solving using some algebra skills here for that x. And if you just multiply both sides by 35 first in order to get rid of that 35 in the denominator on the right side, you will get 42 equals x minus 630, and then you add 630 to both sides, and you'll get 672 equals x. So the score that has a z-score of 1.2 standard deviations away is 672 on this particular test. All right, so that's about it for that section. If you have questions, please ask. That's what I'm here for. And I may or may not see you, quote unquote, in cyberspace.